This is lecture 12 in digital circuits. So in this lecture, I'm going to start the second unit in digital circuits. So which consists of Boolean algebra and logic gates or logic functions. Now, when you see the present scenario, the 80%, 90% is only in the digital domain, right? So the remaining maybe 10% or 20%. So it will be analog. Now, when we deal with this digital system, so these digital circuits which will only understand either 0 and 1, so only two values, not more than this. So either it will understand either 0 and 1 or logic level. So 0 represents some 0 voltage, 1 represents some 5 volt or 1 volt, right? So depending on these logic levels only, it will understand this any function is understood by this only two values or two levels. Yes or no? Now, when we design these different types of digital circuits, so what the designer will try to see is, so what is the cost of that circuit? So it may be any bigger circuit or a smaller circuits. Always we try to see the cost of the circuit. Now, who will decide the cost of the circuit? So the number of components or number of gates present in the circuit, right? Now, when we realize those circuits in a simple way, suppose one operation is required 100 gates or 100 transistor components, right? Now, how to simplify those gates or components to minimize the number of components or number of the gates, so in a simpler way, and it will become a simple circuit. Now, how to do this? So to reduce the other cost of the circuit or simple the realization of a circuit, so we need some set of rules or a set of theorems, right? So that is given by the Boolean algebra. So in 1854, George Boole developed an algebraic system now called Boolean algebra, right? Now, if you see the ordinary algebra, when we learn the linear algebra, right, in our mathematics, so there we have seen some different types of theorems or set of rules. Similarly, when we deal with there are only two values, which is 0 and 1, so we should follow some set of rules and set of theorems. Now, when you follow those theorems, so now we can reduce the cost of the circuit, or we can simple the realization of the circuit, right? So that is this Boolean algebra, the why it is developed, right? Now it is containing its own rules and regulations. So we'll deal with first that one. I will give some definitions first. So Boolean algebra is a system of mathematical logic. Remember, so mathematical logic, right? So it always deal with the logics only, right? Now, and it is defined with a set of elements. Remember, with a set of elements and a set of operators. So it will contain some operators. So only based on those operators, it is the overall algebra and Boolean algebra is defined, and a number of axioms or postulates. So this is some definitions we need to follow. When we follow these postulates or axioms, so we can build a logic function, right? So we can analyze the logic functions, bigger logic function, right? So we have to use elements, operators, and these axioms. So we can simply say theorems also, no problem. Now, what are these elements? So set of elements, only two elements, which is 0 and 1 only. Now we'll have operators, three operators, two binary operators. So binary operators means, so we'll have one operator is R, and R function or simply R operator, and AND operator. So R operator denotion by plus. Sometimes we'll have different
notations. So textbooks, or if you try to write a program, so you'll have different R operations. So sometimes we will use simple this one, right? Or the union of this also we can use, or some textbooks they will follow this also. For AND operation, we have either dot or intersection, right? Or simply sometimes they will follow the ampersand symbol, right? And symbol. This is our, sometimes they will use single and sometimes they will use double ampersand values, right? So different notation. But for this digital circuits, these two, either plus operation and dot, that is enough. So the dot means multiplication and plus means addition, but it is not perfectly addition and multiplication. Anyway, we'll see later now. These are the two binary operators we will use. So if you know these operators and the theorems behind this or and, then the operations is over. We can easily simplify the any logic function. One unary operator, so only it will deal with the one value, either 0 or 1. So it is a not operation, or we can say invert also, invert, right? So these are the operators and these are the elements. Now what are the postulates or theorems that we have to see, right? Now what are the axioms and laws of Boolean algebra? Now these axioms or postulates of Boolean algebra are a set of logical expressions upon which we can build a set of useful theorems, right? So one by one we'll see. So when we do the AND operation, so we need to follow some theorem or some axiom, some postulate. So it will deal with some logical expressions, right? So that we'll see. Suppose if it is an AND operation, so what is the first axiom or postulate is, suppose, so we have two operations, right? So 0 into 0, so which will give the 0 only. That is the first axiom. The second one is, if 0 is multiplied with 1, so what is the value? You will get 0 only, right? So actually it is not multiplication, so either 2 1 false, etc. So anyway, that will deal with later. So I will give a very clear explanation why it is becoming 0, etc. Then one more is, so it is just now we are finding the laws or axioms in Boolean algebra. So when we are going for AND operation, these are the axioms we need to follow, right? Next one is, suppose 1 into 0, again we will get 0 only. One more is 1 into 1, which will get 1 only. So these are the 4 axioms or postulates when we go for the AND operation. Similarly, when you go the OR operation, so 0 plus 0 is equal to output also 0, so equal to also 0. Second one is 0 plus 1, which will become 1. The third one is 1 plus 0, again it will become 1. And the third one is 1 plus 1 will become 1. That is the axiom or postulate, right? 1 plus 1 is equal to 1 only. It's like this. True. So there are two conditions, both are true. So ultimately the overall condition also will be true, right? So that is like this, right? So anyway, we'll see later. So these are we need to remember. Anyway, this is very simple, so you can remember easily. Now one more is NOT operation or invert operation. So it's very simple. When you take, so how to define our notation for this invert operation is 0 bar. This is one type of notation, or sometimes they will use 0 bar also, right? This one generally we use for, suppose there is some a, so we can use a dash, right? Or sometimes a bar. So we can use alternate. Sometimes they will use this one, sometimes they will use this one. So 0 bar or 0 dash is equal to, so opposite. So opposite means 1 we will get. Similarly, if I take 1 bar or 1 inverter, I will get 0. So these are the two axioms for the NOT operation, right? Once we know these 3 operations axioms, so the entire digital circuit is over, right? Always we'll try to see these operations only. So like a truth table, functional tables, right? Now finding the logical expressions, etc. Right? So this is very clear. If it is clear, then it's very simple when you find any logic functions. Now we'll see some difference between Boolean algebra, right? Ordinary algebra and binary number system, because there is a lot of difference between these 3, either number system, binary number system, or ordinary algebra and Boolean algebra. So what are those differences? We'll see. In Boolean algebra, suppose there is a plus a or x plus a, x plus x, y plus y, etc. Then in Boolean algebra it will become a only, right? Example is, so if I take 1 plus 1, the output is also 1 only, right? This is in Boolean algebra. Similarly, if I multiply it with a into a, I will get a only. And see why it is like this is, so in our Boolean algebra, a means either it will take one value, either 0 or 1, right? Like a logical values, not the integer values, right? Only logical values. Now see here also a into a means a only. That is 1 into 1 means 1 only in Boolean algebra. Whereas in ordinary algebra, so it has each and a element is having some significance, right? Number wise. Suppose a plus a means in ordinary algebra it will become 2a. In a into a it will become a square, x into x, x square, y into y, y square, and so on. That is 1 plus 1 is nothing but you will get 2 here. Anyway, same means 1 into 1 means 1 only. If it is a 2 into 2, we'll get 4, etc. Right? So this is the ordinary algebra. Now in binary number system, what we'll do? Suppose if I take 1 plus 1, it is not 2. What is the equivalent? It is 1, 0. Yes or no? Now that is about this one. 1 into 1 plus 1. So anyway, 1 into 1 in number system also, when you multiply, you will get 1 only. So that is another case. So 1 into 1 will get 1 only. Right? Multiplication. Anyway, 1 plus 1 is not 2 or not 1 as in Boolean algebra. It is 1, 0 in binary number system. Right? This is some difference between this. I will see some more axioms or postulates in Boolean algebra, something like this, using again same see the OR operation or AND operation. So don't say addition, okay? It's a OR operation only. So logical operations. So in Boolean algebra, always you say logical operation or logical values, either 0 and 1s only, right? Now, if so, generally we represent the variables in the uppercase letters, capital A, capital B, right? Sometimes we use either small x or small y, right? So anyway, we can use any variable, but generally if you find any standard textbooks, so they will use capitals, right? Capital X, capital Y, Z, etc. Or sometimes, rarely they will use small, which is x, y, z only, right? Now if we do the OR operation between some variable x and 0, so we'll get the x only, right? So we can easily tell x can be either 0 or 1, right? You can take, suppose x is equal to 0. So what is 0 plus 0? So from the OR operation axiom, so 0 plus 0 is nothing but 0 only. And if I take 1, so 1 plus 0 is again 1 only. So whatever we are taking x, we are getting that value. So that's why x plus 0 is equal to x. Anyway, so I think everyone knows what. Still, if you are studying the first time this digital circuits, for those students I'm telling like that. If it is x plus 1, it will become 1, not x. Remember, what is the reason is, if I take x is equal to 0, so 0 plus 1, so what is the axiom? 1 only. If I take 1, 1 plus 1, again it is 1 only, right? So x plus 1 is equal to directly, whenever you see 1 plus anything in Boolean algebra, it will become 1 only directly. No need of no thinking, other thinking. Next, so this one we have already seen, that is in Boolean algebra, some a plus a is equal to a only, right? So this is again x only, x. Now you can verify, if I take x is equal to 0, so 0 plus 0, it will be 0. If I take x is equal to 1, so 1 plus 1 is equal to 1 only. So it is nothing but x. Remember, when you substitute, suppose x plus x is there, if I substitute x is equal to 0, so both here and here it will be 0. It should not like if I take x is equal to 0 here and it will be x is equal to 1. So that is not the case in Boolean algebra, right? If x is equal to 0 means, so we should not take x is equal to 1 at that particular moment, right? So at a time it will take only one value, not here one value, not another value here, right? So x is equal to 0 means 0 plus 0 only. 1 means 1 plus 1 only. So it will become x. Now this is most important, these two, x plus x bar is equal to 1 only, right? So this is very, very important axiom. When we do simplification of any logical functions, there generally we use this type of the theorem or axiom, that is x plus x bar is equal to always 1. Reason is, if I substitute x is equal to 0, so 0 plus x bar, that is 0 bar, that we have seen how, what is the 0 bar, that is invert of the 0 is nothing but 1. So if I take x is equal to 0, this will become 0 plus 1. I will write here, so x plus x bar is equal to 1. How? If I substitute x is equal to 0, so it will become 0 plus 0 bar. We know that 0 bar means 1, so 0 plus 1, what is the value? It will be 1. Similarly, if I take x is equal to 1, so it will become 1 plus 1 bar. So anyway, 1 plus anything in Boolean algebra, it will be 1. So anyway, 1 plus 1 bar means it will be 0. So again, it is 1. So whenever we substitute either x is equal to 0 or x is equal to 1, always we are getting 1 only. So what is x plus x bar, or a plus a bar, or b plus b bar, anything like this, it will be always 1, right? Similarly, if we go for this one, the AND operation, x into 0 always will get 0 only. You can verify 0. If I take x is equal to 0, so 0 into 0 0, or 1 into 0 0 only. Similarly, if it is x into 1, we will get x, right? Here it is 1, but here x. Reason is, suppose if x is equal to 0, what is 0 into 1? We will get 0. If x is equal to 1, 1 into 1, again 1. So whatever the value here we are substituting, that value we are getting. So x into 1 is equal to x, a into 1 a, b into 1 b, etc. Now what is x into x? This already we have seen. So it will be again x only, right? So you can substitute 0, 0 into 0, 0, 1, 1 into 1, 1 only. So x into x, x. What happens to x into x bar? It will be 0. You can verify. So here x into x bar is equal to how much? Now if I substitute x is equal to 0, so 0 into 0 bar, 0 into anything, it will be 0. Or 0 bar means 1, 0 into 1, 0 only. If I substitute 1, so it will become 1 into 1 bar. What is 1 bar? Is nothing but 0, right? So invert axiom. So 1 into 1 bar, 1 into 0, which is 0. So whatever values, only two values, right? Either 0 or 1. When we are substituting 0, we are getting 0. And when we are substituting 1, we are getting 1. So what is x into x bar? Always 0. A into a bar, b into b bar, c into c bar, and so on. Always it will be 0. And one more the axiom is, if I take, suppose, x complement or x invert. So x invert whole invert or x bar whole bar is nothing but x only, right? This is also we can prove like this. So if I take x is equal to 0, so what is this 0 bar? 0 bar is nothing but 1. If I take one more time, that is 1 bar, what is this value? We'll get 0. So when I substitute x equal to 0, so 0 one type one, if I take one complement, I will get 1. If I take one more complement, I will get 0 as it is. So x bar whole bar is nothing but x only. If I take 1, so 1 bar whole bar. So 1 bar means 0, 0 bar means again 1. So 1 means 1. So that is the reason x bar whole bar means x only, or other notation, x dash whole dash is equal to x only, right? Now it's very easy to remember these properties, right? Just if you observe carefully, you can remember. Or when you do the some example problems, how to now minimize the expressions, so it will be very clear. Don't worry. Now this is very important, identity element, right? So when we are having these two identity elements, we'll have, when we do OR operation, we'll have one identity, that is additive identity. And when you do AND operation, or you can say multiplication, logical multiplication, remember, AND operation or logical multiplication, OR operation or logical addition, you can make like that also. Now when you do this type of operations, it will have some additive identity element, something like this. So what is this identity means? If you take some variable and if we do the OR operation, means with respect to 0, it will become x only, right? And if I do like the 0 plus x is equal to x only. When you do some operation and we are getting some same variable, so this is only possible when we substitute one element is 0. It is not possible when I substitute x plus 1, it will become 1 only. But that will not become identity. So when you do some operation between this some binary value or a logical value, right, 0, and with some variable, so it may be 1 or 0, no problem, but it should get only x, right? So that is the identity element. So what is this identity element here is, what is identity when we do x plus 0 with this element? So this element is the identity. So what is the additive identity? Is nothing but 0. What is the property is, if I do some variable plus and some value, it may be 0 or 1. If we are getting that variable x, then it is an identity. Similarly opposite, so 0 plus x also, it is x only. That is we just now seen, right? Operation wise we can perform also. Similarly, AND operation also will have some identity, so which is not 0, right? So x obviously should be x into 1 means x only, or 1 into x is nothing but x only. So what is the multiplicative identity? Is nothing but 1, right? So maybe rarely they can ask, but this will be helpful when we do logical operations, right? So maybe AND operation or NAND operation. So there I think we have this property, right? So anyway we'll discuss there, but you should remember what is the identity element and what is the operation it is doing, and for OR operation and AND operation what is the identity elements. So for additive or OR operation it is 0, for AND operation it is 1, right? Now we'll see what are the laws obeyed by the Boolean algebra, right? So always we see 3 laws: commutative law, associative law, and distributive law, right? Now what is this commutative law is, suppose if we are doing some operation, so suppose some x plus y, right? So these are the two variables. Suppose if I interchange the locations of this, so if I exchange, we will get same result. That is the commutative law, y plus x, or a plus b is equal to b plus a. Yes or no? This is using the OR operation. And one more is when you do AND operation, that is I can make x into y or y into x, which is not possible in the linear algebra. Yes or no? So when you do the A into B matrix, when you do the matrix A into B, which is not equal to B into A, I think, right? Now similarly, if if A into B, capital A into B, so which is also equal to capital B into A. So this commutative law based by the Boolean algebra. So that is the commutative law. You can verify. Suppose if you take x is equal to 1, y is equal to 1, what is the value? We'll get 1 only. Similarly, either 1 plus 1 or if you interchange also it will be same, right? So you will get same value. So that is this commutative law. Next one is associative law, right? So when you do some operation, suppose if you are grouping, suppose something like this, x plus, now we are grouping y plus z, yes or no? So first I'm grouping this, then we need to do again one more operations which is also equal to, so we can make any groups, right? So I can make like x plus y plus z also. In Boolean algebra you can make a group of x plus z plus y also, so you will get same result. There is no change at all. If I change the variables, that is a plus b plus c, if I make a group of this, and this is one more, so I can make a group of these two, that is a plus b plus c. You can make a plus c plus b also, right? So we can get same values in Boolean algebra. If I use the AND operation, so it will be some x into y into z, right? So I'm grouping this first, right? Which is also equal to, if I make first this, that is x into y into z, or a into bc is equal to ab into c, right? So we can make either dot or without dot also, it will be multiplication only. So in Boolean algebra, so it will obey the associative law also. Law is distributive law. So anyway we know from the linear algebra also, so distributive law is x into y plus z is equal to x into y, that multiplication, then addition, this is plus x into z, right? So this is a distributive law. Or we can say in terms of a and b, so a into b plus c is equal to ab plus ac. So we'll get, if we do like this, so we'll do first addition and then multiplication, right? And first OR operation, then AND operation, or first we will do two AND operation, then we can make as OR operation. So we'll get the same answer, right? Or same logic value. Now this is the one law. So in this also there is one more law we can apply, that is, suppose we can make like this, x plus, suppose yz is there, which is also equal to x plus y into x plus z, right? So these two are also, we can say, distributive law also. Suppose if I multiply, so x into x, so what you will get, x into x plus x into z plus x into y plus yz. Yes or no? So from these 3 I can make some. See, x into x is nothing but x only, so x plus xz plus xy plus yz. Now if I take x common from these 3, so it will become 1 plus z plus y plus yz. What is 1 plus anything in Boolean algebra? It is simply 1 only. This is 1. So x into 1, x plus yz. Both are equal, or LHS is equal to RHS. So this is also one more distributive, either this or this, right? So this is direct approach. That is when we multiply, we will get same as like this. What is the proof? Now I will take logic value. Suppose this is I am proving. Suppose if a is equal to 0, b is equal to 1 and c is equal to 0. Now we will try to make LHS equal to RHS. So first I will take LHS. So it is a into b plus c. So what is a? 0. What is b? 1 plus c means 0. So what is 0 into anything? 0. Now what is RHS? Right hand side. What is this? AB plus AC. What is this? A into b? A is 0, b is 1, a is again 0, b, c is 0. What is 0 into 0? 0 plus 0 is equal to 0. Both are equal, right? So in Boolean algebra, so it will obey the distributive law also, something like this. So we can verify this also. Anyway, we got same expression, right? So it will be equal, right? This is about the 3 laws in a Boolean algebra. Now we will see some theorems in Boolean algebra. Now these theorems are helpful when we simplify the big logical expressions, right? So whenever there are so many variables or literals in any logical expression, we will try to minimize using these theorems, right? Now what is this absorption theorem? So first one is absorption theorem. If it is something like this, some x plus xy is there, right? So here we are having two literals, right? So x and y, always we can say variable also, but generally in Boolean algebra or in digital systems we say always literals. X and y are literals. Now this will be equal to simply single literal, which is x. So it's very simple to prove is, if I take x common, this will become what? 1 plus y. So what is 1 plus y? So if I take y equal to 0, 1 plus 0 is 1. 1 plus anything in Boolean algebra always 1. So it will become what? X into 1. What is x into 1? Is nothing but x only, right? So this is the theorem. Or we can say, if you see anyway, say plus ab is always equal to a only. So the b we can eliminate, right? Or we can absorb. That is the meaning, absorption theorem, right? So b, it will be absorbed, or it is equivalent to directly a. B, we can directly eliminate b, right? This is one. Suppose a, and some one more is there, that is generally it is not in this case, but we have to remember that one. Suppose if it is x plus some x bar y is there, this is also very very important one. So it will become simply x plus y, right? So there is some distribution law we need to apply here is, suppose if it is x plus x bar y or something, we can easily represent this one is x plus one time x plus x bar into x plus y. Remember, this is very helpful when you do simplifying the logical expression. Some a plus bc is there, I will take like this. If some a plus bc is there, so I can represent simply a plus b into a plus c, right? One time b and one time c. Now how it will be equal? See, if I multiply a into a, so it will become a into a plus a into c plus b into a plus b into c. Yes or no? Now a into a is nothing but what? A only, plus this is ac plus ab plus bc. Now from these two I can take common a. So what is it? Will become 1 plus c plus ab plus bc. So again, 1 plus c is nothing but 1 only. So it will become a plus ab plus bc. So what is from a plus ab? Again it is nothing but a, right? So from this absorption theorem, so a plus ab means again you will get a only plus bc. So what is this? This is the one, right? So a plus b c, always we can write either a plus b into a plus c. So this will be helpful when there is some complements, right? X plus x bar y. So I can represent like this. Reason is, so I can represent this x plus x bar y is like in a distributive way, x plus x bar into x plus y. What is x plus x bar? Is always 1. So 1 into x plus y. What is the value? Simply x plus y. So this is some redundant rule we can say, but we can remember like this also, right? X plus x bar y. So we can say make absorption also. This x bar we are eliminating, right? So x plus x bar y is always x plus y. Or suppose a plus a bar b is there. So it will become simply a plus b, right? So these two theorems are very helpful when we simplify the logical or Boolean expressions, right? X plus x bar. Anyway, this is very simple, right? So take x common and you will get the answer. But this one is we need to apply some rule which is like this, right? Distributive x plus x bar into x plus 1. Then only we'll get this x plus 1, right?